This video is a tutorial on MCTDH-X software based on this manuscript on arXiv MCTDH-X, the multi-configurational time-dependent hardtree method for indistinguishable particles software. In the last two videos, I have shown how to use the provided bash scripts to automatically perform the simulations, analysis, and visualization of figure 2 and 3 of the manuscript, and interpreted the files generated during the relaxation and analysis. In this video, I will show how to use a second way to redo the simulations. I will use the provided input files, but instead of directly running the bash script, there will be a more manual operations involved. Meanwhile, I will also explain to you the input variables in the MCTDH-X input files. As an example, I will show you how to reproduce the figure 4b of the manuscript. So this is figure 4b. It shows how the correlation order parameter, or COP, depends on the interaction strength in a system of 6 bosons. The COP is defined by the orbital occupations, so we can read them directly from the nopr.out file and do not need to do analysis. The COP is defined as the sum of the square of the orbital occupations. So now we go to the folder. So in the main folder, all the relevant informations can be found in the README file. And especially in this section 3a. So if you have anything unclear, you can further refer to this section. Now we go into the folder Relax Series Fig 4b. So you can see that in this folder there are two files, an input file MCTDHX.inp and a bash script for parameter sweep. So let's first look into the input file. So this is in the input file. A detailed description of the input file can also be found on the manual. So I open the manual on the website, and now we go to the input of the main program. So now we can see that there is a table explaining what each input variables means, and we can see that they are grouped into 3 groups. The first group is the system parameters, which specify this physical systems, and for example, whether it is a bosonic system or a fermionic system, and also the number of orbitals and number of particles, and etc. The second group of the variables are the DVR variables. This includes that they specify the grids and spatial extension of the simulation. And then there is a third group, which is the integration group. In this group, they specify the parameters related to their numerical integration. A detailed description on the integrators can be referred to in this paper. Now let's look at the input files and look at the input variables one by one. So the first one is job type. So, and the job type determines whether this is a bosonic system and a fermionic system. And then we have m-orb, which is the number of orbitals, and n-par, which is the number of particles. And we also have x lambda 0, which is the interaction strength of the interaction. And now we have this keyword interstrength, which we will later replace it by different values from 0 to 20. And we have the mass of the particles, which is always set to be 1. And we also have the job prefactor. So this is a complex number, and if we are doing relaxations or imaginary time propagations, we want to put it as -1, 0. And if we are doing propagations or real-time propagations, then we will set this number to be 0, -1. Then the guess is to specify the initial conditions of our simulations. For now, if we want to completely start with a random initial condition, then we will use guess equals to hand. If we already have some specified initial conditions and we want to use it so then we would choose guess equals to binary files. This is usually the case when we first do relaxations, and then we use the results of the relaxations as the initial conditions to do the propagations. And if we are using guess equals to binary files, usually we also want to change this binary start time to be the corresponding binary start time. And the next group of variables is the DVR variables. First is the dimension of the simulation is 1, and then we want to divide the grid in the x direction into 512 grids, and we want to start our simulations from x equals to -8 and end at x equals to +8. Our simulations will start at time equals to 0 and end at time equals to 10. And our integration time step would be put to 0.1. And this is the case for relaxation. And if we are doing propagations, usually we will set it to 0.01. And this is the time step for the output. We could set it to be 0.1 or 1.0. And next one is the coefficient integrators. If we are doing relaxations, we would want to use the DAV integrator. And if we are doing the propagations, we would want to use the MCS integrator. And of course, here we have a write ASCII options. If we want to write the ASCII files or orbs.dat and coef.dat files as we are doing the simulations, we would want to put it as true, otherwise we would put it as false. And here is where we specify the potential of our simulations. Now we are using HO1D plus time-dependent Gaussian, and we are setting the parameters as this. So a list of potentials can also be found on the manual. The potentials are listed in the predefined one-body potentials in the appendix, And now we search for our H01D plus time-dependent Gaussian. So basically it has the form like this, and we can see that P1 is the harmonic trapping the trapping frequency, and then P2 is the center of the harmonic trap, and then we also have P3 and P4 are the magnitude of the barrier and also the ramping time, and P5 is the center of the barrier, and P6 is the width of the barrier. And you could also search for other look for other potentials that you want in this table. Other than using the predefined potentials, we can also define new potentials by ourselves. This more advanced technique can be done in the source files of the MCTDH-X. So here, MCTDH-X release is the main folder of the program. And now we want to go inside into the folder source and init get gas pot. In this folder, now we look for this get one body potential file, and we go inside. Now we want to look for H01D plus TD Gauss. So this is how we define the potential H01D plus TD Gauss. And if needed, you could also define your own customized potential. And finally, we have the interaction. When we are claiming interaction type equals to 0, then we are using a contact interaction. And likewise, there are also a list of interactions. You could find it also in the manual. And you can see that we have different kinds of interaction. For example, the Gaussians, contact interactions, and then contact interaction with time-dependent strength, and so on. So here is a list of interactions. And also likewise, if you want to modify the interactions, you can also do it in the same folder, MCTDH-X release source init gas pot, but in a different file. This time is in the get interparticle potential files. For example, here, this one is how we define the Gaussian interactions. One thing I have to notice is that the interaction is defined by two flags. The first flag is interaction type. The second flag is which interaction. They are all specified here. So you can see that by defining both flags, we can define one interaction. Next, we look at this bash script for the parameter sweep, parameter sweep.sh. In this bash script, the first two lines are to verify that the aliases are working, and then the next few lines are for the definition of the parallelization. And then we want to use bincp to copy the executables, the GCC files and the library into the folder. And then for I from 0 to 20, we now want to create folder strength I, and then we copy everything, including the input files and the executables and the library into these folders and go inside the folders. Now we want to use this sed command to replace the keywords in the input files, enter strength, these keywords, by the numbers from 0 to 20 in each folder. So now we have specified the interaction strength for each simulations. Next, we want to use this eval exec to execute to run the MCTDH-X. And after running the MCTDH-X, as I said before, what we are interested are only in the orbital occupations in this case. So we want to copy the last line of the NOPR files and collect the NOPR files from all simulations into one file, which is nor.out file. So, and in the end we go back to the main folder. So this is the procedures. So if now we don't run the MCTDH-X for the moment, and we execute the bash script, now we can see that we have created a lot of folders. And for example, now we compare the input file, the original input file in that we have provided with an input file that a random input file, for example, 15, strength 15, the input file in this folder. So we can see that the two input files should be exactly the same, except that now in the original input file there is this keyword enter strength, but in the new input files that is already in the folder strength 15, this keyword should already be replaced by number 15. So in this way, we are able to simulate systems with different interaction strength and then collect the orbital occupations from each simulations. So now we want to run the bash script with running the command MCTDH-X. Now we have finished our simulations, and all the results or the NOPR.out files from each simulations are collected in this file, NOR.out file. And let's look at this file. So there are 21 rows in these files, and each row corresponds to one simulation or one interaction strength. So it is from 0, 1, 2, 3, and so on. And in each row, the orbital occupations are reported from the second entry to the second to the last entry, which means that the 11th entry. And so now we want to look at the COP, the correlation or the parameter, which is defined by the sum of the squared of all these terms. So now let's try to plot it. So now we want to plot the NOR.out file using so this is the sum of the squared of all these entries as a function of interaction strength. So now we can compare this result with the results in the manuscript. So we can see that it is exactly the same curve. So in this video, I have shown you how to do a parameter sweep with our provided bash script and explained to you the variables inside the MCTDHX.inp input files. And in the next video, I would focus on this figure 5a. The difficulty in this figure is that when we are doing relaxations to look for this ground state, there is another excited state with energy very close to the ground state. So the system could be easily trapped inside these excited states during the simulations. And we will introduce a way to circumvent this situation.